That was our early solar system, and this is the early Earth right here. And the Earth, after all that crazy activity of it forming and everything, basically went through phases like this. And so it started off as a very hot ball of rocks and things like that, and all that stuff smashing into it really heated things up and melted everything. And then it started to kind of cool down and form a crust around the outside. And so if we were to look on the inside with some sort of X-ray vision, we could see the inside like this. And so I want you to think of this like a cookie that's been taken out of the oven recently that is warm and gooey on the inside, but has formed a little bit of a crust on the outside. And that is what our Earth is like right now. And that's really important because that means our Earth is still in formation, that it is still moving around and doing things. And we're going to see what kind of stuff that causes. Don't forget that red slides are where you have to take notes. You should have your notes handout ready to go. Don't forget to look for the owl and let me know where he is. And remember to fill in all of this stuff that you see here. So take a look at this picture. This is kind of interesting. These are the deepest holes that human beings have ever dug. So if we look at this in comparison to the size of the crust, so here is the deepest hole that humans have ever dug. And the crust of the Earth goes all the way down to here. That's just the crust of the Earth. That's just the outermost layer of the Earth. So the question then is, if that's as far as we've gone, how do we know what the inside of the Earth is made out of? How could we possibly know this? So what is this a picture of? Well, I know it's a picture of a pencil and a glass of water, but what's going on right here? You may know this. This is called refraction. And this happens when waves get bent because they're going through different mediums. Mediums is just like the substance that they're going through. So this is going through, this part is just going through air. This part is going through air and glass. And this part is going through the water and the glass, right? And so the different densities of these substances cause the waves of light to get bent. Well, what does this have to do with the Earth? Well, what kind of waves go through the Earth? Think about that for a second. What kind of waves go through the Earth? Well, how about earthquake waves, right? Earthquake waves go through the Earth and they get bent in exactly the same way. All waves get bent when they travel through things of different densities. So we can actually measure this and measure how they get bent. So if there's an earthquake over here where this is starting from, and we have some seismographs over here and over here and over here, all sorts of places on the Earth. We have thousands and thousands of them also all over the Earth these days. So we can basically measure how those waves get bent as they travel through these different substances and where they end up on the other side of the Earth. And we can measure the density and things like that. And from that, we can get a lot of knowledge. We can understand what kind of elements it's made out of. We can even understand things like temperatures and and whether they are a solid, liquid, or a gas at that temperature. So we know the material of the interior of the Earth based on how earthquake waves move through the planet. That is one of the main reasons why we know what the interior of the Earth is made out of, because as I showed you before, we have not really dug down to see what's in there. That's really more or less the only way we know. There's a couple other ways, but that's really the main way that we know. So, what are the layers of the Earth? I bet you know this. Help me out here. What's that one? The crust. What's that one? The mantle, that one, outer core, and last but not least, the inner core. Okay, so label this on your notes. The inside part is more hot and dense, and the outside part is less hot and dense. This layer is about 1,000 kilometers. This is about 2,000. This is about 3,000. This is a really rough estimate here, but I like to use these numbers because they're pretty easy numbers to remember. 1,000, 2,000, and 3,000. They're not too far off from the reality of things. The crust is only about 5 to 70 kilometers. 5 kilometers at its thinnest, 70 kilometers at its thickest. And I want you to think, where would it be the thinnest and where would it be the thickest? Well, think about it. In the mountains, it's very thick, right? And the ocean is basically the lowest area of land. So in the oceans, that would be where it's thinnest. That's going to be important later, so keep that in mind. Now, as we talk about layers of the Earth, I want you to understand that it gets a little bit complicated. We're going to try to keep it simple here, but one of the reasons why it gets complicated is because we can talk about the layers in terms of what they do. And when it says response to stress here, really what they mean is how liquidy or how solid they are. Is it really solid like the crust? Or is it more of a liquidy kind of substance, or is it someplace in between like Play-Doh or something like that? So we can talk about the layers in terms of what they do and how they behave, or we can also talk about the layers in terms of what they're made of or their composition. You can see that when we go by the composition, we really only have three basic layers. We have the crust, we have the mantle, and we have the core. If we go by the response to stress or how liquid they are, then you get some more. We divide it up into some more layers. So as we're talking about this, I might talk about something like the upper mantle and lower crust area or something like that. So understand that when I'm talking about that, I'm talking about it in terms of how it's responds to stress or how liquidy, how much it flows. So why does the Earth have these layers in the first place? Well, when the Earth first formed, you saw that in the beginning of the video, it was basically this big ball of lava. So just like when you've put something into a liquid, like drop something into water, the heavier things tend to sink to the bottom and lighter things tend to float to the surface. Well, that's exactly what happened as the Earth was forming. The stuff sinking to the center of the Earth was the more heavy, or what we should say is the more dense things. And so things like iron, gold, stuff like that, stuff that's really heavy and dense actually sinks to the center. And so the lighter things, things like oxygen and stuff like that, tend to float to the top layers of the Earth. And remember, when you drop something and it sinks, it's sinking, it's falling towards the center of the Earth, right? So when something sinks in the actual Earth, it's going to go towards towards the center, and things that are lighter are going to move towards the edges. That's really what we mean by up and down, right? Up is kind of away from the Earth, down is towards the center of the Earth. So when you think of this, now we're not really gonna talk about it in this way, but I really like to think of the idea of the atmosphere as really being the top layer of the Earth, because that's where all the really light stuff, things like hydrogen and helium and some oxygen and stuff like that, nitrogen, those kind of things, really kind of floated to the surface, and that's really, you are in the upper layer of the Earth. The atmosphere is just the top layer of the Earth, but we're going to kind of leave that separate. So we have the inner core. The inner core is solid iron and nickel, and that's kind of an interesting thing. It's really, really hot enough to melt that stuff, but because there's so much pressure on it, it keeps it as a solid. So the center of the Earth is really a solid iron ball. Now, as we move out, the outer part of the core, that's going to be liquid iron. It doesn't have quite enough pressure on it to keep it solid, so it actually melts and becomes liquid. Now, the mantle. In the mantle, we can kind of separate the mantle into the mesosphere, which is most of the mantle, and this is going to be actually mostly solid stuff here. This is solid silicates, and you should remember silicates from when we talked about minerals. And then we have the asthenosphere. Try saying that with me, asthenosphere. That is the upper mantle, and that's kind of this sort of semi-solid, gooey kind of stuff. Think of it kind of like that kind of consistency. Okay, then we get to the crust, and the crust, again, we can kind of break down into parts. These are going to be mostly solid silicates, so things that are made of silicon, oxygen, things like that. That's actually what the rocks of the crust are made out of. There's your silicates. Remember talking about those when we talked about minerals. And we have two different types of crust. We have the oceanic crust, which is thinner, and the continental crust, which is like deep dish pizza. Think of it like thin crust pizza and deep dish pizza. And remember what I said, where the mountains are, that's the thicker crust, and where the ocean is, that's the thinner crust. Kind of looks like this, right? And we can see that the crust under the ocean is thin, and the reason why we have mountains is because that crust gets thicker there and kind of rises up like that. Thin crust in the ocean, deep dish in the mountains. And finally, we have what's called the lithosphere. And this part is really important because this is the crust plus the upper mantle part. And that's where things that's the part that's kind of riding on top of the asthenosphere, which is that gooey part. And so that kind of allows things to move around a little bit. All right, so what we have here then, see if you can name all these things. We have the ocean crust, we have the continental crust, we have the lithosphere, we have the lithosphere there. Notice the lithosphere is much thicker in the continental areas. And we have, what's that part? The upper mantle. Okay, so another thing that we need to know about the layers of the Earth is that the spinning inner core creates a magnetic field around the Earth. And there still is a little bit of mystery about how this works, but this is what makes compasses work, north and south poles, and it also protects us from harmful solar radiation. This is really important. If we didn't have this magnetic field, we really wouldn't have any life on Earth. This is, in every way you think of it in sci-fi movies, this is a force field. It stops us from getting hit by rays of radiation. So this is kind of like stopping us from getting hit by laser beams and stuff like that. It really is like a force field that the Earth has, just like in all these sci-fi movies. Force fields, force fields, force fields. So can you please draw and label the Earth's magnetic field? Notice that we have a magnetic North Pole and a geographic North Pole, which are different because the magnetic pole of the Earth kind of moves a little bit, but we don't move the geographic North Pole. We kind of keep that in the same place. So the electromagnetic field protects the Earth from charged particles, and it also creates the aurora borealis, or northern lights. And these are some really beautiful things to look at. So let's take a look at them. So this is something that I have told you throughout the year that this would come up several times. So hopefully you remember what this is. Do you remember what this is? Yeah, this is convection. Convection, remember? So hot air, hot things rise, cold things sink. We talked about this when we talked about meteorology. That's basically what causes weather. We talked about this when we talked about the sun. There's the convection layer, the convective zone in the layer of the sun. And now we're going to talk about it in terms of layers of the Earth. So this is what causes the Earth to move around. This is what it's like on the inside of the Earth, under the crust. And it causes the crust to kind of move around, as you're seeing in this animation here, so that it is being separated in certain parts where the magma is especially hot and rising, and then it separates and moves apart. And so you have parts where there is new crust being created, and then on other sides of that crust, you have crust that is diving back down into the mantle and being reheated and remelted to be recycled. And that causes this to happen. The entire surface of the Earth to kind of move around. This is called plate tectonics. The Earth's crust and upper mantle are broken up into sections called plates. Oh, hold on a second. What's the crust in the upper mantle called again? Oh yeah, that's right, the lithosphere. Right, so the lithosphere is broken up into sections called plates, and these plates float on the mantle like rafts, and they're moving very slowly, so you don't really notice it, but you are sitting on a moving surface right now. Now, I got a short little clip here for you that shows some lava that is doing this. Now, understand that this is not really plate tectonics that's going on here, but it is the same process on a smaller scale. In this clip, you can actually see the sort of crust forming on the top, and you can see how they move around and how parts of it get made new and how parts of it get kind of taken away and remelt. So the process that causes this plate tectonic movement is called continental drift, and this is the gradual movement of the continents across the Earth. And it was proposed by this guy that you see here named Alfred Wegener. He was German, so just like Volkswagen, we pronounce the W as a V. So in 1915, the German geologist Alfred Wegener, who lived from 1880 to 1930, proposed this idea of continental drift. It wasn't actually accepted until the 1950s. And if you look at when he lived, that's kind of a sad story because he came up with the idea, but nobody really believed him on any sort of large scale until well after he died. But he's the guy that came up with it. And basically, he came up with it. The first thing he noticed was that some of the continents seemed to kind of fit together like puzzle pieces. And he found this very interesting, and that's what kind of got him going on this path. So the speed at which these move is about the same speed that your fingernails grow, and that's why you don't notice it. It's the same thing as you don't really notice your fingernails growing. Like you can't sit there and look at your fingernails and watch them grow and see it happening. Same thing happens with the tectonic plates. So what is the evidence to prove that this is happening? Let's talk about the different pieces of evidence. Since this is happening so slowly and we can't really see it happen in real time, we need to figure out what the evidence is that this is actually happening. So, as I said before, the first piece of evidence was that the edges of all the continents kind of match up like puzzle pieces. They seem like they were fitted together at one point in time. It is important to understand that it's not the coastline like what you see as the edge of the continent on a map. It's actually about a mile or so out to shore where you have what's called the continental slope right here. And if you guys remember the movie Finding Nemo and the drop off in Finding Nemo, right? Well, that's what they were talking about, the continental slope. All of this scientific stuff in Finding Nemo was actually very accurate. And so that's the continental slope, and you can picture it like how it was portrayed in the movie. So a second piece of evidence is that the same fossils are found on different continents. So this is very interesting. Notice, okay, so this is this creature right here. Okay, and the fossils of that creature are found in this area. Now, obviously, all of these continents have been kind of stuck together the way that we think they were a long time ago, but notice how they match up, right? It would be very strange for this type of animal to be found on two completely separate continents that are separated by an ocean, because these guys don't swim. So how would they get from one place to another unless these were connected at some point in time? And same thing for all of these other ones. Look at the fossil records of this guy here. They stretch from here through here. We actually find them on this small island here. We find them on this area here, in this area here, and in this area here, just in the right places that they line up, so that if we put these puzzle pieces together the way they fit, that all of these fossil records also line up perfectly. Same thing here. We have this creature, fossil records of this creature that we find in this area of South America and this area of Africa, which now are separated by an entire ocean. And again, these aren't swimming animals, so they didn't swim across the ocean. It was that this part of South America was actually connected to this part of Africa a long time ago, and they have since moved apart from each other. Another one is very similar to that. We find the same rock structures on different continents. So if we look at something like this, these are the Appalachian Mountains, which you should be familiar with because they go through Virginia. And then we also have the British Isles right here, and we have the Caledonian Mountains in this area. And these all have very similar features to them. They're made out of the same type of rocks, they were formed in the same way, and all that kind of stuff. And so these also fit together. So this part here would actually fit right into this part of the puzzle piece right here. Okay, here's our next piece of evidence. What is this a fossil of? Take a look at this. You see these little leaves in here, right? What do you think that's a fossil of? That looks to me like some sort of fern or something like that. So where would you expect to find something like this on the planet? What kind of environment would you find this in? Well, if I had to take a guess, I would say some sort of forest type of area, right? Like maybe even a tropical rainforest or something like that. Well, you know where we found these? Yeah, Antarctica. And so the only way that this could possibly happen, remember, warmer areas are near the equator, colder areas are near the North and South Pole. So the only way that this really could happen, it doesn't have a lot to do with climate change, because even though the climate changes over time, the North and South Pole have always basically looked like this picture here. They've always been cold. So plants like this wouldn't be able to grow in that area unless that area was actually near the equator at some point in time and has moved more towards the poles. So fossils of plants and animals in Antarctica is another piece of evidence that we have. This one is both one of the most hard to understand pieces of evidence and one of the most convincing pieces of evidence. So see if you can understand this. So this is magnetic layers in the sea floor spreading out. So in order to understand this, what we need to understand is that as this magma comes up through here, it's filled with little pieces of iron, okay? And when it is melted, the iron is sort of free to move around however it wants. It's a liquid substance, so the iron can kind of move around. Once it gets up to the surface here and cools and freezes and hardens, it becomes the little piece of iron get locked into place, and then they start to move in this direction as those plates move, this way and this way. Okay, so they're locked in place now. And so the magnetic poles can shift fairly suddenly, and I have the word in fairly in quotation marks here because it takes thousands of years, but that's pretty quick on the time span of how long the Earth has been around. So right now, north is in the Arctic. The North Pole could shift to someplace else. So what happens when the poles shift and they flip over is that all those little pieces of iron, just like a compass, get lined up in a certain way. So for a time being, when they come up to the surface, they all kind of get locked in place this way, maybe, okay? So that they're all facing that way. Well, if the magnetic pole changes, maybe they get all lined up this way. And so what happens is you get these alternating bands of all of the particles being lined up one way, and then they are all lined up in another way. And the reason why that's happening is because they get stuck in place, and then that part moves aside a little bit. And then the magnetic pole changes, and they get stuck in place this way. And then that part is kind of next to this part here and moves along beside it. So you have pieces that are lined up this way, here, and then that kind of moves aside, and you have pieces that are lined up this way. And then you have pieces that are lined up this way, pieces that are lined up this way, pieces that are lined up this way, and they alternate. So, and the only possible way that that can happen is if we have this crust forming and moving along. So this is Earth. Looks a little different though. I mean, what continent is that? That's not North America. It's not Asia. Huh. So this is Pangaea. Pangaea is the supercontinent. This is when all the puzzle pieces were fitted together before they all separated from each other. So this is when all of the plates were once together. This is the supercontinent known as Pangaea. Now, it is also important, that's probably the most famous one, but there was actually ones before that. There was continents called Gondwanaland and Laurasia, and these were two megacontinents that were around even before Pangaea was around. Now, this brings us to the idea of the boundaries of these plates. So each one of these, you can kind of see a plate here, right? And these guys are the plates that are moving around. And the edges of these plates are where all that magma and stuff is coming up, like we've seen. So we have the Pacific plate kind of moving in this direction. We have the Caribbean plate moving in this direction. We have the Nazca plate moving in this direction. And so you could imagine that right here, these plates are moving apart from each other. And this is kind of what we've seen. But over here, we have this plate moving this way. And so these guys are moving towards each other. So we got to kind of figure out what is happening here. And you can imagine that there's basically three different ways that these plates could be moving relative to each other. They could be moving away from each other, and that means divergent. They could be moving towards each other, or convergent. Or one could kind of be moving that way and the other one's moving that way. They're kind of moving sideways to each other, and that's called a transform boundary. So we need to kind of talk about all these. All right, first of all, remember, two types of crust, right? Thick crust and thin crust. So two types of crust. We have the ocean crust, which is more dense, so it sinks. It's made out of a lot of basalt. You should remember that. Remember that is an extrusive igneous rock. So that is basically a thinner and more dense crust that tends to sink. And then we have continental crust, and this is kind of less dense. It's made out of mostly granite and stuff like that. So that's going to tend to kind of ride up on top of the oceanic crust. So which one's ocean, which one's continental? Yeah, there we go. Thick crust is continental, thin crust is the ocean crust. So which plates below do you think are ocean plates? Take a look at it. Can you find them? Looks like that one is an ocean plate, right? That guy's an ocean plate. So we have a couple of different ocean plates there, or areas that are kind of all ocean plates, but you can also talk about this area as being kind of like an oceanic crust. That area. Okay, so let's start off with divergent boundaries. These are the ones where the crust is created as two or more plates are pulling away from each other. This is the one where they are moving apart from each other. Looks kind of like this. You have these plates moving away from each other, and as they move away from each other, well, you can't just have nothing there. The lava is going to come up and it's going to fill that gap, and it's going to cool and harden and form new crust there. So we have the newer crust near the center, and the older crust is further away from the gap there. It's about 4 miles thick. Now, this creates one of the biggest, most important features on the entire Earth. And you may have never even heard of this because it's under the ocean. But this is actually the largest, by far, the largest mountain range on the entire Earth. Think of it like the seams of a baseball. It kind of runs around the Earth very similar to that. Now these guys are moving apart from each other, and as they move apart, right in this little area here, you have all this magma that's bubbling up to the surface and hardening and basically forming an underwater volcano. Right along that line there. And so I want to show you a quick little clip here that is an animation of what this really looks like from down underneath the water. There you go. So please label that in your notes as the Mid-Atlantic Ridge. And so at the Mid-Atlantic Ridge, I want you to think about the fact that these guys are kind of spreading apart from each other, right? They're moving apart there, those two plates. But what that means is that those two plates are colliding into each other. And so what do you see there? Well, you see a mountain range. Well, we need to talk about why that happens. That is our convergent boundary. So this is where crust is destroyed and recycled back into the interior of the Earth. And depending on what type of crust you have here, you can have some different features happening here. So one plate is going to dive underneath. So if we have an ocean versus continent area where they are converging, this is called a subduction zone. And this can create a very large trench. This is like a really deep valley. And in fact, the lowest place, kind of the opposite of Mount Everest, the lowest place on Earth is called Mariana Trench. And that's an example of a subduction zone. Take a look at this little clip on the next slide here to see what a subduction zone looks like.
White Island, as with all of New Zealand, sits right on the rim at the junction of the Pacific and Australian plates. It's a collision area where the floor of the Pacific Ocean, Australian plate, in what is called a subduction zone. The seafloor is buckled and pulled down into deep trenches, and the friction triggers powerful earthquakes as the Pacific plate is slowly consumed. Even here, water volcanoes, as rocks are melted and recycled. White Island is one of a chain of volcanoes that includes the notorious Tarawera.
That was quite a bumpy flight. But it's worth it because we're right on the Pacific Rim, aren't we?
We are. This is the Pacific Ring of Fire at its best. There aren't many places where you can see it so graphically.
So we're literally walking to the edge of the Australian plate and right in front of it.
Well, not quite going that far. I mean, we really are entirely on the Australian plate here. But this is where we feel the effects of the downgoing Pacific plate.
Now, sometimes when you get two plates coming together and converging, you get mountain formation. These basically crumple the land up and make it rise up to form mountains. These are all examples of it. The Sierra Nevada mountains are a really good example of this. You can see it in map form, you can see it from an aerial view, and you can see it from kind of a side view. These were formed by two plates coming together. The Andes Mountains were formed this way by one plate coming this way and another plate coming this way. That includes Mount St. Helens. We've seen Mount St. Helens before. It's a volcano that erupted. So, the Ring of Fire. Maybe you've heard of the song before. The Ring of Fire is a zone of frequent earthquakes and volcanic eruptions that encircles the basin of the Pacific Ocean. So here is the Pacific Ocean. And basically the Ring of Fire goes all the way around the Pacific Ocean, and you tend to get a lot of basically movement between the plates there, and so you get a lot of volcanoes and earthquakes happening in that area. So the ocean versus ocean convergence. This tends to create archipelagos. These are a group of volcanic islands that are formed from ocean crust convergence. There's an archipelago right there, a little line of islands. This is the Antilles Islands in the Caribbean, again, an archipelago, and a big part of Alaska is an archipelago created by this. Indonesia was created by this, and you can see all of these volcanoes here. Each one of these little marks here, these little icons here is a volcano, is an active volcano. So that's a lot of volcanoes. And then we get continental convergence. This is where we form our mountains. So the Indian continental plate is crashing into the Asian plate, causing mountains to form. And they're still growing. In fact, Mount Everest is growing by about an inch every year. There we have the Himalayas, which includes the tallest mountain on Earth, Mount Everest. That's what it looks like from a side view. They really are some pretty marvelous. So continent divergence. These are when the continental plates are moving apart, and they are going to form features like this. The Red Sea here is an example of continent divergence. When you think of this, I want you to think of like if you take like a Milky Way candy bar or something like that and pull it apart, you get that kind of thin, gooey caramel layer in between there that's very thin. That's kind of like what's happening here. And so you get features like this where the crust gets kind of stretched, and so it becomes very thin there. And you tend to get valleys and seas and things like that. So here is what the Red Sea looks like. And you can see this guy here kind of standing on one edge of the plate over here, and the other edge of the plate would be over there somewhere, and they're kind of moving apart from each other and causing this crust to get kind of stretched apart and thin. All right, well, that's about it. We will talk about all this in class. I know that was a lot of information there, but we're going to go through those things one by one in class, and I will see you then.